Usually when you think about a car crash, you focus on the moment of impact, the crumpled steel, the shattered glass. It's violent and it's incredibly visible.
Right, yeah. But that visible wreckage is, well, it's really just the finale.
Yeah.
Because if you look at the material engineering side, the actual failure of a steel frame starts in total invisible silence. I mean, it happens on a microscopic level long before that ultimate catastrophic snap.
Which brings us to the mission for this deep dive. We are looking at a highly technical 2026 engineering paper that figures out exactly how and where materials crack. Specifically, we're examining asymmetric three-point bend
It
specimens.
sounds dense, I know.
It does. But the reason you should care is that preventing everyday structural disasters like the steel frame of your car giving out relies entirely on mastering this precise mathematics.
Exactly. And before predicting a crack, we first have to understand the microscopic chaos happening right before a piece of metal gives out.
Okay, let's unpack this. We have to talk about the plastic zone. Think of it like bending a cheap plastic ruler. Right before it snaps, there's that one spot that turns white and bends totally out of shape.
Yeah, we've all seen that.
The stress concentrates in that specific core area around the crack tip, deforming it before it breaks under what's called mixed mode loading.
Right, and within that loading, you have different forces attacking the material.
Like what?
Well, you have mode 1, which is physically pulling the material apart, and then mode 2, which is a sliding or shearing force. Think of it like rubbing your hands together.
Ah, okay.
The researchers here specifically tested interstitial-free steel. That is the highly formable steel used in the body of your car. And they wanted to see exactly how it behaves under these combined forces.
I have to push back here, though. I mean, we have been building steel structures and predicting fractures successfully for decades.
Sure, yeah.
Why do we suddenly need a new 2026 paper to tell us how steel breaks? Like, are the old models broken?
Well, they actually were getting the crack angles wrong under these really complex combined loads.
Wait, really?
Yeah. Earlier models just assumed that the plastic zone at the tip of a crack was just a uniform circle. But it is not. This brings us to a new standard called the Generalized Minimum Plastic Zone Radius, or GMPZR. The major discovery here is that a crack actually initiates precisely where this plastic zone is the smallest, not where it's the largest.
Oh, wow, that feels completely counterintuitive. I mean, you would think the biggest area of deformation is where it would break.
It does sound backward. But think about pressure. If you press against a balloon with your flat palm, it just stretches.
Right, of course.
But if you press with the tiny point of a needle, it pops.
Oh, that makes so much sense.
Yeah, the smallest area of that plastic zone is where the stress becomes the most intensely concentrated. And that is exactly where the crack fires off.
So why did the old models miss that?
Older models failed because they completely ignored something called T-stress.
Okay, what exactly is T-stress doing to the metal?
Imagine a secondary, invisible hand gently stretching the metal sideways, parallel to the crack, while the main forces are trying to snap it.
Okay.
Older models treated that side stretch as harmless background noise. But by factoring in that T-stress, the GMPZR predicts the exact angle a crack will shoot off far better than anything before it.
See, understanding T-stress sounds great for a controlled lab, but engineers designing cars need practical tools in the real world, right? They can't run endless computer simulations for every single bolt and panel just to find the T-stress.
Exactly. And to solve that, the researchers ran heavy finite element analysis.
Which is what?
It is essentially putting the material through extreme virtual torture tests. And they proved something vital. Mode I, that pulling apart force, is by far the most dangerous.
Oh, interesting.
Yeah, it generates a stress intensity almost 20 times higher than the sliding mode 2 force.
Here's where it gets really interesting, because all that complex virtual modeling didn't just give them more data, it gave them a shortcut that completely simplifies the engineer's job.
What's fascinating here is that the researchers found a perfectly linear, proportional relationship between the normalized GMPZR and the stress intensity factor.
Right.
When they mapped it all out, the microscopic chaos just formed a straight line. They calculated a simple constant slope of 0.0035.
Meaning an engineer doesn't need to fire up a supercomputer anymore.
Exactly. Now, engineers can use a quick equation built around that 0.0035 slope. By just plugging in the loading angle, they can instantly predict the crack direction.
So for you, this means safer cars and stronger structures, and all because researchers distilled the unpredictable chaos of tearing metal into a beautifully simple tool.
It just proves that even the most complex microscopic failures have an underlying order.
It really leaves you wondering, If engineers can distill the chaotic, microscopic initiation of a crack into a simple, predictable mathematical slope of 0.00035, what other seemingly unpredictable physical failures occurring around you are actually hiding a simple mathematical rule waiting to be discovered?